The first law of thermodynamics. The first law of thermodynamics expresses energy conservation in a thermodynamic process relating heat, work, and internal energy. James Prescott Joule, after whom the unit of energy is named, was a brewer and also a physicist and mathematician. From 1840 to 1849, he conducted thermodynamics experiments using some of his brewing equipment to raise the temperature of water in a thermally isolated container by doing mechanical work on the water. He found that 4.2 kilojoules of work raised 1 kilogram of water by a temperature of 1 Kelvin. It was previously known that adding heat could increase the temperature of a body of matter, but this showed that work could do the same. Work was doing what heat was known to do. At about the same time, scientists and engineers showed, on the other hand, that heat could be converted into work in a steam engine. Therefore, heat and work are not separate, but related, and this led to the idea that both heat and work are forms of energy. We have previously seen that a system contains internal energy, but does not contain heat or work, which exist only during transfer. Recall that heat is non-mechanical transfer of energy, and work is mechanical transfer of energy. The first law of thermodynamics applies to all matter, but we will focus on an ideal gas. First, let's look at work done by an ideal gas on a piston. A fixed quantity of gas is enclosed in the piston cylinder. The gas is sealed in the cylinder, although the piston can move back and forth, so the volume V of the gas is variable. The gas has pressure P and exerts a force F on the piston plate, which has area A, so pressure P is equal to F divided by A. We assume that the force is just enough to push the piston slowly to the right. If it pushes it through a small distance dx, the gas volume increases by dV equals A dx and does work F dx on the piston. Here we are finding the work done by the gas, hence the subscript by. We could also consider the work done on the gas, which is the negative of the work done by the gas, but we will stick to looking at work done by the gas. So the work done by the gas is F dx, which is equal to PA dx, since F equals PA, and since dV equals A dx, we see that dW by is equal to P dV. So this dW equals P dV is the work done by the gas on its surroundings due to a small increased dV in its volume. Note that work can be positive and negative. If the gas expands, then dV is positive and dW is positive. But if the gas is compressed, then dV is negative and dW is negative. In this case, the gas does negative work, so positive work is done on the gas. We consider the small amount of work dW rather than just saying work equals pressure times total change in volume over a process, because the pressure can change during a process. Therefore, in general, to find the total work done during a process, in which the volume changes from an initial value Vi to a final value Vf, it is necessary to add up the small amounts of work done at each step in the process, which is to integrate dW over the process, which is to integrate P with respect to V. The integral under a curve is the area under a curve. So on a PV diagram, the work done in a process is the area under the curve of pressure as a function of volume. The direction of the process is important. Directed to the right, the process is an expansion, so the area under the curve is positive. Whereas in a compression, the direction is to the left, and the area under the curve is negative. An important property of work done by a gas is that it is path dependent. This means that the amount of work done in a process between an initial and a final state depends on the path taken between them. Here are two processes between the same endpoints. Since work done is area under the curve, it is clear that the work done following the yellow curve above is more than that done following the red curve below. When a gas does positive work, it loses energy, so its internal energy decreases. When a gas does negative work, it gains energy, so its internal energy increases. So the change in U, the internal energy, is equal to minus W by. As with solids and liquids, adding heat to a gas changes its internal energy such that delta U equals Q. In a process, there can be heat added to the gas and work done by the gas, and they both change the internal energy in accordance with the first law of thermodynamics, which is delta U equals Q minus W by. This is for a thermodynamic process that follows a path between an initial and a final state and expresses energy conservation. For an infinitesimal step with infinitesimal quantities, du equals dq minus dw by. Now U, the internal energy, is a state function, since it is a function of the state variable T, the temperature. We have said that the state variables are P and V, but T is also a variable, and it depends only on the state since it is a function of P and V. If you know the state of the gas, you can determine the value of U. You don't need to know the path that the gas followed to get to that state. However, on the other hand, W by is path dependent, and the first law shows that Q also must be path dependent. Since U is a state function, its difference delta U between two states is fixed. But W depends on the path, so Q also depends on the path. We can see this another way if we express Q as the sum of delta U and W. If delta U is fixed and W depends on the path, then Q also depends on the path. This formula will be very useful to calculate the heat added in a process, because whereas delta U and W can usually be calculated, there is generally no easy way to directly calculate Q. The infinitesimal form of this formula for a small step is dq equals du plus dw.